How many R's in strawberry? You can see 3. Every big model used to say 2. That gap has a name, tokenization. It decides what the model can actually see. You see 10 letters. The model never does. For strawberry, one widely used tokenizer breaks it into 3 tokens: stachar, and berry, sealed packages, not letters. Here's what's coming. The sealed packages, building vocab, where it breaks, and price and limits. Never written a line of code? You just use these systems? Then this is for you. By the end, you will look at any odd spelling slip and explain exactly why it happened. And you will see in advance when a prompt is about to cost more than you expect. 5 stages. First, the itself and what the model actually receives. Token 1, stage 1 R. Token 2, 0 R's. Token 3, berry, 2 R's. 1 plus 0 plus 2 equals 3. Tokenization, an episode of the AI Actually series. The title this episode pays off. Why AI can't count the R's in strawberry. The model never saw your letters. Stage 2, sealed packages, what the model actually receives. Think of a shipping warehouse. You never count individual screws inside sealed boxes. You move whole boxes. The model works the same way. It never receives the raw letters you typed. It receives sealed packages called tokens. A token is a common chunk of text. The system has learned to treat it as one unit. A token can be a whole short word, or just a piece of a longer one. And sometimes it's only a single character. Those are the sealed packages the model actually receives. Here is why the count is hard. The model doesn't unpack by default. Its internal map for each token is a single point in a high-dimensional space that encodes meaning and usage patterns, not a list of the letters inside. Asking it to count letters is like asking a librarian who only ever handles sealed books to tell you how many times the letter Q appears on page 47 without opening them. Today, most say 3. They just memorized this one question. Nothing about how they read changed. The split still bites on words nobody drilled. The takeaway, the model never saw your letters. It saw 3 sealed chunks. And that number is useless on its own. You need to know how those chunks got chosen in the first place. That's stage 3, building the vocabulary. How does the system decide which chunks become tokens? It uses a method called byte-pair encoding. Start with every single character and byte as its own tiny token. Then look across a huge pile of real text and find the pair of tokens that sit next to each other most often. Glue that pair into one new token. Repeat. Glue the next most frequent pair. Keep going until you have a vocabulary of roughly 50,000 to 100,000 tokens. Common words and word pieces stay whole. Rare ones stay broken into reusable parts. It's exactly like a typesetter who notices that T and H appear together constantly, so they cast a single TH block to save time. Then they notice THE is common and cast a THE block. The final set of blocks is efficient for everyday English. It's not designed for counting the strokes inside any one block. Why do it this way? Pure letter by letter would make every sequence far longer and slower. Whole word only would explode the vocabulary with every rare name and misspelling. Subword chunks hit the sweet spot, short enough to handle novelty, long enough to keep meaning. The cost is that letter-level facts become buried. The takeaway, tokens are the frequent pieces the training data rewarded. And that design is exactly why letter counting, rhyming, and digit arithmetic stay fragile, which brings us to stage 4, where it breaks. Letter counting fails for the sealed token reason you already saw. Rhyming needs the sound or the ending letters. Those live inside the tokens. Arithmetic on multi-digit numbers is worse. The number 12,345 often becomes several tokens, not one clean value with place value. The model pattern matches rather than calculates. That's why writing numbers out in words sometimes helps, and why single-digit tokenization experiments improve math scores. The root is the same sealed packages. Try a word the internet has not hammered. Ask how many L's are in paralleled, or how many times exactly the letter S shows up in a made-up product name. You will still see the old slip. The mechanism never left. Only the celebrity example got patched by memorization. The takeaway, any task that needs the inside of a token is fighting the design. And that same design decides how much you pay and how much text fits, which brings us to stage 5, price and limits. Every API call is priced by tokens. Tokens in and tokens out. Rough rule of thumb, one token is about 4 characters. That's roughly 3/4 of a word in English. Output tokens cost several times input, so verbose prompts burn money fast. The context window is the maximum number of tokens the model can see at once, prompt plus reply. Common sizes run from roughly 8,000 up to 128,000 or more. Exceed it, and the oldest tokens fall off or the call fails. Long documents, big code bases, or chatty histories burn the budget fast. That's why people summarize, retrieve only relevant chunks, or switch models. You can now open any free tokenizer playground, paste a prompt, and see the exact chunks and count before you send it. That one habit stops surprise bills and catches letter-level traps. The mistake beginners make is ignoring the count until the invoice arrives or the model truncates. Tokens aren't free and they aren't letters. You can now explain why a model once said 2 R's in strawberry and still fails on fresh letter tasks. It never saw the letters, only sealed tokens built by merging frequent pairs. The stakes of not knowing this are wasted money on bloated prompts and misplaced trust in spelling or counting answers. Homework. Pick any 3-word product name you like. Predict how many tokens it will become and where the letters hide. Then check it in a public tokenizer tool. Did your prediction match? Next time we look at what happens after the split. How the model actually chooses the next token. Models read sealed chunks, not letters. That's why counting R's was ever hard. So next time an answer looks off, A, ask it to spell the word out first, or B, hand the job to real code. Tell me which you'd actually do. And subscribe for the next one.